So for this video, we're going to talk about mostly parametric surfaces. Flux integrals is mostly going to be discussed in class. But just to give a little motivation, let's suppose we have some vector field F, and for flux integrals, it's going to be easiest in terms of visualization to think here of F giving the velocity of a fluid, say, flowing. So at F of x, y, z is just the velocity of the fluid at the point x, y, z. So just think of this as measuring how a fluid is flowing through space. And then we can consider some surface S. And a flux integral, which we're going to develop this in class for what it is and how it comes about. But for now, we can just think of this as the flux integral is measuring the amount of fluid flowing through our surface per unit of time. So this is something we might be interested in measuring. So think of like blood flowing through a blood vessel or something like this. And this flux integral is going to measure this. And so for us, our interest for this flipped class video is we're going to develop and study flux integrals in class, but what we need to do to evaluate them is we're going to have to take our surfaces and parameterize the surfaces. There are some simple cases or special cases where we can evaluate the flux integrals without having a parameterization of the surface, but in general, that's going to be the easiest thing to do. So just to recall when we were calculating, say, work using a line integral, we developed this without using parameterizations, but then in order to actually evaluate a line integral, we parameterized the curves. You can see this picture here is the same one that was given in the class on parameterizing curves. So you can see this arrow here is the r of t, and as the t moves from A to B here, the tip of the arrow is tracing out our curve. And that's what we use when we were parameterizing curves with vector valued functions. So a curve is a one-dimensional object, a surface is two-dimensional. So while we just needed one variable t to do a curve, we're going to need two variables to do our surfaces. So the idea is we want to do the same thing for a surface and have a parameterization of it. So for surfaces, the variables are usually denoted u and v. You don't have to do that, but that's kind of standard, so that's what we'll mostly stick to. So what we're looking for now is a vector valued function where we input two numbers and output a vector. So we input u and v, and we output this vector where the coefficient of the I vector is xuv, yuv is the coefficient of j, and zuv is the coefficient of k. And now for when we parameterize curves, we just had our t in some interval from A to B, but now we can have some region in two space. So u and v is going to be in some region R that's in two space. And what we want is, as I go over all of the different UVs in this region R, these vectors R, UV should give all of the points of the surface S. Just like before, the tips of the arrow should give points on the surface. So just like with curves where there isn't kind of some uniform way to do it, it's best to just see a bunch of examples, and the more examples you do, the better you get at parameterizing surfaces. So we'll just do a few here. And obviously, as we do flux integrals in class, we'll have to parameterize a bunch more surfaces. So let's start with something somewhat simple. So suppose I just have a disk here, and this is just the disk where my x and y are inside a circle of radius 2, and my z value is just fixed at 2. So this surface would satisfy z is equal to 2, and x squared plus y squared should be less than or equal to 4. So remember, x squared plus y squared equals 4 would give us a circle of radius 4, but we want all the radiuses up from 0 to 4, so we take that less than or equal to 4. So when we're thinking of our functions for our parameterization, the easiest one here is z of uv, because since z is always 2, we don't want that to change. So z of uv should be 2 for all of the u and v values. So that's particularly simple. Now for the other part, we need to parameterize. How do we parameterize a disk? So recall to parameterize a circle of radius a, we would just use r of t is equal to a cosine ti plus a sine tj, and we let 0 be less than or equal to t less than or equal to 2. But here what we need to do is we need to let that radius vary, because we want a disk, so we want all the radiuses from 0 to 2. So to do that, we can, instead of taking a fixed radius a, we'll let that radius be u, which is a variable, and so our parameterization can be u cosine vi plus u sine vj plus 2k. And that 2k is just, of course, because we wanted our z value to be fixed. And now notice for each value of u, you're getting a circle of radius u because that v is going from 0 to 2. So just think of starting with the point when u is equal to 0, you're just at the point 0, 0, 2. And then as u gets bigger, you're just kind of expanding circles out to get all of those different radii. And so if we want to phrase this in terms of the region R here, our u and v satisfy u is between 0 and 2, that's our radius variable, and v is between 0 and 2 pi, that's our angle variable to get all of the circle. So here's kind of a picture of what's going on. So we can see this is our starting at our origin here and going out to a point on the surface. And we can just see these circles here in our parameterization. Each of those circles is a fixed value of u. So you're fixing the value of u and doing a circle, fixing another value of u and doing another circle, and you just fill out the whole surface that way. So a surface that will come up often and is very easy to parameterize is if we just have the surface given by z is equal to f of xy. So we saw this in curves as well. If you had like y is equal to f of x, that was a particularly simple curve to parameterize. And same thing here if we have some surface z is equal to f of xy. So in this case, the parameterization we can give is just ui plus vj plus f of uvk for u and v and r, and that r was whatever our region here for our surface was. So those ones are always very easy to parameterize, so we love it when we get those surfaces to work with. Let's try one more surface to look at here. So let's consider a cylinder here. So it's x squared plus y squared equals 4, and we're going to let the z values go between minus 3 and 3. So if you remember how to graph something like that, it looks like this. This is our surface S here. So just think of it as a circle that we're dragging. Start down there at z equals minus 3, and we just drag a circle of radius 2 upwards until we get to z equals 2. And that's our surface. So let's think about how we would want to parameterize this. Well, just like how I described the cylinder, we want to think of a circle of radius 2 in the xy plane, and then we want to move it up and down start down at z equals minus 3 and move it up to z equals 3. So to do that, we can parameterize the circle. So we take the circle of radius 2, so that would be 2 cosine ui plus 2 sine uj. And so that would give us a circle of radius 2 in the origin. And now to make sure we get all of those z values, we just put v to be our variable in front of k. And then our region here is we just want to let u go between 0 and 2 pi, so we get all of the circle. And then just let v go between minus 3 and 3 to make sure we move that circle from minus 3 in the z value to up to 3 in the z value. So that gives us a few different surfaces to parameterize. We won't be really looking at any surfaces that are super complicated to parameterize, but we'll be doing more in class, so we'll get some more practice at this.